Now we have a motion along this path in the space. You can see this is the position vector of the point, and this is the velocity vector, and we would like to determine a point at which, if we turn the engine of the space vehicle off, then the velocity vector should be pointing to C, so that the vehicle is able to coast through C. What we mean is this: look at the motion. So here, if we just keep on moving, notice this, that if the engine is turned off at this point, then what happens? Acceleration is 0. So the velocity is constant, and then what's going to happen is this, that as the vehicle moves along this direction, we will be able to coast through the point C. So what we need is this, that in order to be able to coast through this point C, this vector V and this vector PC should have the same direction. So for example, see, this is our vector P and this is our vector PC. So if they are in the same direction, then the vehicle would be able to coast through C. Alright, now let's do an example to illustrate this. That's on page 880 of Calculus 5th edition by James Stewart. What they do is that they give us the position function of a spaceship by this, and we have to find out that when should the engines of the spaceship be turned off so that it is able to coast into a space station that is located at the point 649. So just for curiosity, let's look at a graph of this motion, and we can just plot the points, go to rectangular, and here is a graph. And what I did was this: I already made many different variations of that for you. Here I changed the scales, and then I plotted the location of the space station. You can go ahead and play with that. You can rotate it and see how it looks by different views. Okay, all right. Well, that's not the point right now, so let's go back to our calculation. So this is our position vector. We differentiate the components to get the velocity vector. The space station has the coordinates as 649, and here is the picture of what we want to do. So in case we are able to determine a point for which we should be able to coast into this space station, then we should, in order for the availability of that point, we should be able to get a positive number mu, so that we have this equation satisfied. Okay, so we know that the coordinates of C are what? C 6, 4 and 9, and those of P are 3 plus T, 2 plus natural log of T, and this value. So if we take their corresponding differences, then that's what then what will happen? We get the vector PC. Now, in order for PC to be in the same direction as we should be able to get a number mu, so that this equation is satisfied. And all I have done is I have multiplied mu into this vector to get the components like this. Now, in order for these two to match, we should have each component equal, so we get a set of 3 equations. Now all we have to do is we have to see if we are going to be able to find values of T and mu that satisfy all these 3 equations. Okay, now here our job is pretty easy. We have mu equals 3 minus T. We can go ahead and substitute that in any of these 2 equations, and we are going to use technology to solve these. So this is less writing. So what I did was I replace this mu by 3 minus t here. Okay, let's go ahead and ask the package to solve it. We'll try to solve exact, because even if we are a little bit away from the space station, we are gonna miss it, right? Okay, oh, it says no solution found, and that's a little strange, but well, packages do that, because I think if you inspect it close enough, we can see a solution. So anyway, let's try graphing it, and if we graph it, you can see that t equals 1 is a solution, and just substitute t equals 1. The equation is an identity. Okay, so there should be something that we can look at later, but let's see if there is another solution that might be there. And yes, there is another solution, 16 point something. Alright, so we have t